So welcome everybody. Good to see so many known faces and also many new faces. What I wanted to do first is actually in the first 30-45 minutes is to give you a kind of overview and the plans for the semester. Is it okay if I speak in English? Because I know that there are people from many different countries. And obviously I'm not a native English speaker, which means I do have an accent. So if something is unclear, don't hesitate, okay? So what I wanted to give in the beginning is just some basic information, because I also know that there are many of you who have not taken courses at the University of Oslo. So there are some basic things which can be useful. So the typical setup is that you have a official website. And on that website, so there's a lot of duplication of information here. Right? The official website is the one where we will put in messages. You're going to get these messages by email. So I typically send a weekly update about plans, etc., etc. And then you will find this in Canvas as well, which is a interface which the university uses, and many you're probably familiar with that. And that's where we will hand in the projects, etc., etc. So the teachers is actually this guy here. This is the one you have in front of you. In Norwegian, there's a pretty funny name, but every language has a lot of funny last names. So I grew up in Italy, and Italy has really a collection of funny last names. One of my best friends was actually called the one who eats goats, Mangiacapre, which is a pretty funny name. And then Ruben is one of the TAs, and Uda as well. So in the lecture plan, the official one, we don't have a lab session, but then we introduce that by popular request. So for those of you interested, we can have sessions after the lectures, and Uda and Ruben will be there as well, but not today. Today, what I thought is that those of you who have the possibility, we can just sit, just go into the lab session and just chat about possible projects. If you want to introduce yourself, we can do that. We won't do the introduction now because we are pretty many. You will also see that the lectures, in case you cannot be here physically, you can attend via Zoom. So this course has actually been tailored also to people who are in the full-time jobs or people which are at other universities. So we have people from NTNU, we have people from the University of Southeastern Norway, we have people from the University of Bergen, and they obviously cannot attend in person. The lectures will be recorded. So that means that if you don't have the possibility to be here or be there on Zoom, you can always watch the lecture again. So it's definitely not Hollywood quality, but hopefully it just gives you a kind of faithful reproduction of what we did. Okay? Now, here you will also find the schedule. And for those of you who have taken courses here, you can subscribe to updates under the schedule. So in case there are changes, change of room or whatever, then you will get an email. So take a look at the schedule as well, because you can actually subscribe to updates there, either by email or by text. Then there is a GitHub site. So if you scroll down here, you will find the GitHub site here. And this is where I basically put all information. Now, the GitHub site is, you can actually pull down the information here, download it on your laptop. I am assuming that you're familiar with any of these version control softwares like Git. So GitHub is just a provider where you can store files. You have GitLab if you prefer that. You can use Bitbucket, and some people even use Dropbox. Now, GitHub works with Git as a version control software, and these are things which we will not talk about in the lectures or in the lab sessions. We assume you know this. So if you don't, then you should team up with somebody who can teach you that. Sorry for that. So you can download everything, and typically I update the weekly slides during the weekend. And that means that you will find an update on a weekly basis. And you can then, by a Git pull, you can then just get the latest update. Alternatively, you can always fork the repository and just use this as your notes. So please feel free to use these notes as you want, okay? Can you hear well in the back? Sometimes I tend to mumble a little bit. I also need to have this headset because my laptop has a weak microphone. And since my brain is linked with my legs, I keep moving. And then the microphone, I need these ones. So that means also that when you ask questions, you need to raise your voice a little bit because this actually reduces already a bad hearing, okay? So you can find the information here, and you will also find a weekly schedule. And what I thought of doing now is actually to go through things. So in the weekly schedule here, you will see an update later where we have the video of the lectures and also whiteboard notes, which will be added right after the lecture. You will also find the videos and the whiteboard notes, which is my blackboard. If you go in here after the lectures, you will typically find a link here as well. So a lot of information. So there are many, at least 3 channels by which you will get more or less the same information. So what I want to do now is to switch to the basic layout of the course. So if we now just switch to the slides here, let me just do that and find them here. Here we are. So basically today, I mean, the first minutes now, we were going to look at the different layouts and possible themes for projects. So I should also say a little bit, this course was actually a self-study course till 23. But then since so many people have enlisted, we also decided to have regular lectures. So previously we would just meet on a weekly basis and discuss projects. But then we decided that we should also offer this as regular lectures, but we want to keep the spirit of the self-study path. And I will say a little bit more about that. So some of the textbooks which we have, basically all the textbooks are textbooks you can download for free from the university library. And in the beginning, we are going to remind you about deep learning methods. So this is not a course where we teach you to program a neural network because we assume that you've done this. So today I will just repeat things which many of you have seen before when it comes to the setup of a neural network. So a neural network is actually the basic building stone in many of the deep learning methods, whether they are discriminative or generative, or if you go to reinforcement learning, you go to large language models. I mean, at the heart, there is a neural network in some way or the other one. So many of you, so let me ask, how many of you have actually programmed either yourself from scratch or using PyTorch, TensorFlow, or the libraries, a neural network? So how many of you? Good. So the first lecture is basically just a reminder of how we do that. And then from next week and on, I will try to explain to you how we're going to progress, okay? So I want to keep a lot of flexibility here. So we have lectures, which you already know about. We have lab sessions. So the first regular one will be next Thursday. But today, I thought for those of you who have the time, we could just sit here and chat a little bit and discuss possible paths for the projects. I'm also going to give you some homeworks for next time, which we will discuss actually. So we plan to work on 2 projects, but you can opt for just one long one. So if you do 2, each counts 50% of the final grade. If you do a long one, that's 100% of the final grade. So these are options which you can choose from when it comes to the type of paths you want to choose actually. There's no exam. and you will find all information on the GitHub site. So the tentative plan for the first half of the semester is actually to go a little bit more behind the mathematics of deep learning. So these are the topics. Some of these topics have been covered in a course called Physics STK 4155, which is Introduction to Machine Learning. But we will discuss a little bit more actually how to write your own program here, because there are people who, as a project, they would like to write their own CNN code. That is a full semester project. Alternatively, we have people who have written their own recurrent neural network code, which is also a full semester project. It takes time, and it's very easy to make errors and be stuck in down in a rabbit hole for quite some time. We've had people who have actually written their own prototype for a large language models. So RNNs are typically entry points for large language models. And then there's another method which is pretty popular, which is autoencoders, because that also allows us to link with unsupervised learning. So typically we split between supervised and unsupervised learning. And the supervised learning is the case where we have labeled data, which is often very expensive to label data. And the unsupervised case is the one which is more common. So we often have data, tons of data, and we don't know exactly what it means. Then I'm not so sure if I want to say something about transformers. We'll come back to that. And then there is another very, very important aspect, and I will try to say the difference between generative and discriminative methods. So I will say something basics, and then we have very popular models. So if you look at softwares like DAL-E, somebody may have used that one to make figures. So they're typically diffusion models are some of the central models for generative models. And these are typically the topics which we have been covering. Now, if people are interested, so I actually do research on reinforcement learning applied to quantum mechanical systems. So my cup of tea is more quantum mechanics. And reinforcement learning is actually one alternative, but we may not cover that fully in the lectures. So which means that this is a topic more for self-study. Then what I'm going to do, since this is a course which is more designed to the natural sciences, and every year we've had roughly a third of you who are partial differential equations aficionados, okay? And PINS is one of the standard methods. And that when I'm starting to discuss neural networks, I'm going to tailor the discussion to the solution of differential equations. And that's going to be a project as well. And we are going to look at one specific differential equation, but you can replace that with your favorite ones. So we are going to look at something which is called the Black-Scholes equations. Anyone familiar with that? Only one of you. That's actually, it was a Nobel Prize to Black and Scholes in finance. So it's a stochastic diffusion equation, which has been used to model the option market. And we are going to look at how to solve that with physics-informed neural networks. If you don't like the Black-Scholes, you can replace that with a diffusion equation, the Navier-Stokes, or your favorite equation. So I will use differential equations as the example. So some of you will prefer to apply this to classification problems. We will discuss that as well. So, and then there's actually the course I would like to teach. So, I mean, it doesn't mean that this topic, the topics here are not that interesting, but this is really interesting. So I will not have time to do that. But if you want to follow that path, take a look at these lectures. They're just excellent. So there's a lot of room. I want to keep the flexibility in defining projects. This is really a fantastic way by which to do science. I actually use these tools on a daily basis. Then there are topics which we'll also not cover, which deal with Bayesian statistics. So how many of you have a background in statistics and have heard about Bayes' theorem? Okay, so it's a good fraction of you. This is also a topic I will not cover. However, when we go back to generative methods, this is actually us baking in a probability distribution. And many of these methods are actually based on Bayes' theorem. So you will get Bayesian statistics in one way or the other one into the generative methods, which we will teach. So one of the reasons for having chosen these basic methods is that when you move to, let's say, agent-based AI, or you're looking at reinforcement learning, at the heart of these methods, there is one of these guys inside. So you could say, why don't we just teach about reinforcement learning, which is perhaps a much more interesting type of machine learning for actual research. One of the reasons is that it's important to know what enters into the black boxes. And this is essentially what we will pay attention to here, the basic mathematics and the basic ingredients behind discriminative and generative methods. So it means that what we want to give you is a basic understanding of some of the central methods, which then you can build more fancy stuff with. Does that sound okay? Any questions so far? Okay. So these are just some textbooks. You can download them for free. And actually the textbook by Goodfellow, and some of you may have heard Benjo when he came to Oslo last year. He gave a seminar for the opening of the one of the AI centers, which is called Trust at the University of Oslo. And he is seen as one of the really central persons in the development of artificial intelligence and machine learning. So we want to keep this path open. So some of you may have specific interests, things which align with your master thesis, your PhD thesis, or if you're in a full-time job, there may be some of these topics which align with your job, and you want to update yourself about these topics. So we want to have that path fully open for those of you who are interested in that. So in a way, it's we are going to be roughly 40, 50 here. So it's a kind of big task actually to tailor the projects to each one's individual needs. But I like doing that. And this is what gives me something back, because if we have 40, 50 people, I can think of you like AI agents in a certain sense. And you're doing things which I would never have the time to do. So I learn a lot by reading the projects. And I like to see this project as entry points for publications. So we've had every semester, we've had cases where the projects have aligned with somebody's master thesis or PhD thesis and can end in a publication. Actually, some of the projects which I propose can become publications. And we had one of the projects which we are going to, actually this PINS project we're discussing is a paper we are writing up now based on the project from last year. I'm not pulling your legs. I like to have that kind of option open. So the project options. And we have two possibilities. You can do a one semester project, or you can choose to do two projects. So this is very much up to you. And we are going to use the first lab sessions to actually discuss these things. So at the end, let's say within 2 to 3 weeks, you have a kind of rough idea of what you want to do. I will, however, align project 1 and project 2, if you think of two separate projects, with the lectures. And in the first part of the lectures, these are roughly the methods which I will focus on. And that allows you to design different projects. So let me show you the possibilities. So this is essentially what I want to do now before we start reminding ourselves about neural networks. So the one which is pretty obvious, this is what I call the physics-informed neural networks, which is really tailored to people who actually do their research in partial differential equations. So how many of you are thinking of doing something along these lines? Okay, yeah, it's a good fraction still of people. Good. So that's going to be something which I'm going to suggest, and that's going to follow essentially the neural networks path. And you can choose the different partial differential equations, how you can use neural networks to solve differential equations. So that's how I will actually refresh and discuss neural networks with you. You can obviously use them for many, many other problems, classification problems, etc., etc. Then we also have, when it comes to coding, you can choose what you want to do. You can choose language. We had people who actually wanted to develop things in Julia. So last year, we had one who wanted to develop a reinforcement program in Julia. So that's fully possible. So this is very much up to you. And one thing you should think of, obviously, somebody wants to write their own codes from scratch. But in many, many cases, you have these very efficient libraries which allow you to actually address questions which are close to your research without you having to spend half a year to write the program yourself. So it's always this balance, right? So the course here gives you the knowledge about what the methods are about. And then the programming part is something which we leave to you, in a sense, to decide which path you want to take. Okay? Any questions about that? So how many of you are familiar with Python? That's a good fraction. How many are like Julia or other languages? Good, excellent. So the C++, that's also a good fraction. So I'm a C++ and actually Fortran programmer. So this is archaeological times, right? I'm an old guy. For the first part of the semester, we have, if you're looking at classification problems, so how many of you are thinking of doing something along a classification problem? I mean, the simplest case is actually image recognition. Okay. In that case, what we can do is actually that you do a first project where you look at the classification problem with the convolution neural networks, autoencoders. If there is a timestamp on, let's say, images, suppose you're looking at heart diseases as a time of function where you have pictures of the heart at different time steps, then clearly, and you want to classify whether this is a candidate for getting a heart attack or not, it's a simplified example, then recurrent neural networks could also be a possibility, because then you have a timestamp and you're looking at the time evolution. So you can do classification problems with recurrent neural networks, obviously, as well. So this could be a typical theme if you do 2 projects, and then you can switch to generative methods in the second project. And then you have the possibility to compare both discriminative and generative methods on the same data set. And then you can assess whether this method or that method are better suited for the data set you have. So that's a path which people have chosen. And I will link to you examples where people actually did that. Then there's a long top list here. You don't need to read everything. Some of you would like to look at the mathematics of deep learning. And I've actually have a path there which people can look at. It's actually a topic which unfortunately is not researched well at a department which should have done it, the Department of Mathematics. So the mathematics of deep learning is really a hot field. So anyone who's would be interested in something like that? Excellent. So that's also another path. So I'm going to just leave this as it stands now, and you go back when we meet next week, then you have thought a little bit more about what kind of paths you would like to take. I mean, I'm not saying that you should decide now, okay? Then some of you are actually interested in high performance computing and actually using GPUs on machine learning projects. So you could say there's some interesting observations. So to enter the field, and suppose you want to have your own startup, is often easy because the software is there, it's freely accessible for everybody, but at a certain point, you meet the wall. And the wall is access to high-performance computing facilities. Because at a certain point, if you're training a large language models with trillions of parameters, there's no way you can do that on your laptop. So like when I use GPUs on high-performance facilities in Norway, I have to pay 5 Norwegian kroner per GPU hour to access the facilities. If you have your company and you're accessing the same facilities, the price is even higher. So that tells you a little bit about the price, because if I use the CPUs, then the price per hour, per CPU hour, is 0.05 Norwegian kroner. It's a factor of 100. But there is also more than a factor of 100 speed up when you use GPUs. To give an example, last year I used 100,000 GPU hours, which translates into 500,000 Norwegian kroner for my own research fundings. So to develop the software is something which is very democratic. Everybody can do it, but then you hit the wall at a certain point. And that's why speed, the efficient utilization, is something which is very important. We will not focus on that in the lectures. However, we recommend that you get an account on the University of Oslo's machine learning nodes. So if you search online UIO ML nodes, then you find access points, and you just write that you want to access the machines and you explain why. And then you will have access to not the latest NVIDIA GPUs, but the previous generation. But that allows you to actually have access to better computing facilities. So it's called UIO ML nodes, and everybody who has a UIO account can have access to this. And I recommend that. So this is one path which you can choose if that is interesting for you. But we will not have the time to discuss that, because we will focus more on the algorithms themselves. Then every year, there have been groups of people who wanted to write their own CNN or recorded neural networks, or even LLM. If you want to do that, I would recommend to write just one project. That's a full semester job. So it's demanding, but it's also very, very rewarding. So in the lectures, when we discuss CNNs and RNNs, I will show you how you can build your own code. So you have a template. So this means building the code from scratch. Anyone who would be interested in that? It's not intimidating. It's a very fun project, but it's very much up to you guys. Then, if we come to the second part of the semester, these are roughly the kind of methods which I will discuss in the lectures. And you can obviously link what you did in project one with that. You can just have one project, or you can make two projects. And this could, for instance, be aligned with a classification project, which includes CNNs and AEs, so autoencoders. So then you could explore different methods on the data sets of your interest. So this will be, you can read more of these details, but I just wanted to give you roughly the kind of possibilities. Then we have the reinforcement learning part, if that is interesting. That is more self-study path, if you're interested in that. You can actually pick up what you did with the physics-informed neural networks. So there is actually a path which aligns here with the physics-informed neural networks. And you can, for the second project, you can actually keep on working with the physics-informed neural networks and just add reinforcement learning to that. But this will be more self-study. We will have less time in the lectures because we have only 2 lectures per week. Then, this is my own hobby horse. So with colleagues, we've developed a new method, which we call parametric matrix models. And we had people last year who actually did that. And you can actually use, what this method actually means is data for training. It needs that. So you can use a solver for differential equations, and you're looking at the time evolution, and you can actually, because many of these differential equation solvers are extremely expensive computationally. So you can just solve the equations for some few time steps and use that as a training data, and then parameterize a low dimensional set of matrices, which then can be used to make predictions for further times. And we've actually been comparing that to solutions of Navier-Stokes equations and also these Black-Scholes equations, and it works extremely well. So that's another possibility. And then clearly, we want to keep the spirit of self-study, which means that many of you have your own hobby horses you want to keep, or your own data sets. So there is a lot of flexibility here for the way we can design the projects. It doesn't mean that you can actually come up with something which is totally different from what we focus in the course, right? It's like you getting an assignment in a language course, and then you say, I didn't like the assignment, and I just wrote about picking blueberries in the woods, right? So there's a limit to what you can do, but we want to keep a lot of flexibility, okay? As long as you use some of the central methods. So I will not have time to cover in full depth reinforcement learning, but if you want to explore that, that is fully acceptable. If you want to look at the AI agents applied to scientific problems, this is something which is also possible, although we will not have time to discuss it. But since I have some research experience, I'm able actually to judge whether what you're doing is meaningful or not. But since we only have 2 lectures per week, there's a limit to how much we can cover. There's a limit to how much I can cook up and explain in a meaningful way, whatever that means. Okay. So I want to give you a first homework. And so we will have the lab session next week, although today we will also, if you want to hang around, we can discuss things. But I wanted you to think over what is your interests and how this aligns with what I presented. It may not happen that what I presented aligns with your interests. And then if you can prepare, let's say 3 to 5 slides, something like that. What we've done every year is that people have presented to all the other ones the things they're interested in doing. And we normally recommend people to work in groups. That is always beneficial. It saves time. And you probably heard my lame joke about working in groups. I mean, one of you may be pretty good at programming, the other one may be good at the scientific case. And then you have somebody like me who's good at making coffee and cracking lame jokes. And so this is the first homework. And it's also an opportunity to find potential partners. Yeah, this is just about, if you go here to this link, you will find project examples from last year and the year before. So take a look at those for inspiration if you want. There are many of them. I'm extremely proud and impressed by what people did. And some of them have actually ended up in scientific papers. So take a look at them, because that gives you a kind of template on how to write the report. So we want the report to be written like a scientific report, which basically means the same as a scientific article. So this is another homework, which I'm giving you. So there is a set of questions here. You don't need to answer them now, but look at them for next time. And what I want you to do now is to see how many of these you think you can answer without too much thinking, okay? So if you look at these questions here, just take a look at them now, because these are questions about background, which we, in a way, are assuming that you have seen, so that we can actually, we don't need to spend time on repeating things which you have done. So if you look at the questions here, how many of you think you could roughly answer these more than 50% of the questions? with some thinking. Okay. Take a look at them. I mean, you don't need to answer them now. So just a brief impression. If you then look at the next one, just take a look at it, and then we will ask the same thing. So these are typical quantities, which I will also repeat a little bit about in the next lecture. How many feel that 50% is something you could answer with some thinking? Okay, lovely, it's good. So let's look at these ones. So optimization is a central part. This is actually, I actually forgot to mention one thing. So in connection with these methods, 2 years ago, we had a group of people from mathematics who wanted to look at optimization algorithms. That is, I mean, the heart of all machine learning, the optimization part. And the mathematics of the optimization part is something which is often not emphasized not emphasized enough. So if some of you is interested in actually looking at that mathematical aspect of, let's say, deep learning methods, that is a very interesting project to look at. So how many of you think that with some, let's say, some thinking, looking back at notes, you could answer at least 50% of these questions? Okay, still good. We are going to repeat these things actually again and again. But these are central ingredients when we're dealing with machine learning methods. What about these ones? So how many feel comfortable with answering these questions without too much thinking? Yeah, still. So with some rebooting of your goldfish memories. Sorry, I have a goldfish memory. I'm not expecting you to have, but I have. So I need constant reboots of my memory. But so I was always provoked when teachers would say, "You've seen this before," because after the exam, I mean, it was just like the mind was a tabula rasa, just everything empty, and you didn't remember anything. And then people say, "You have seen this before." No, I haven't seen this before. Okay, so repetition is always important. So I'm going to skip some of the things here, but I wanted to say a little bit about the things which we will cover. So you will actually see that here we will have a focus on deep learning. For some of you may be interested in Bayesian statistics. We're also going to discuss principal component analysis, but we will not discuss ensemble methods or linear logistic regression, except just to remind you of things. And we will also say something about reinforcement learning. But these methods, 4 and 5, is what I normally call archaeological time. That is before the deep learning revolution. So generative methods. So how many of you can say that you know what a generative method is? Okay, that's good. And if I say discriminative methods? Okay, so still a good fraction, but let me say quickly what it is. So the best way to think of a generative method, and the reason why I like them, is because they give you everything. Well, I shouldn't say everything, but it gives you what you often are interested in. So if you think of a standard discriminative method and the standard machine learning approach, what you typically do is that you have a data set in, and you want to fit a model to that. And then you want to use that fitting model to make a prediction. So this normally leads in statistics to what's called a frequentist approach. Are you familiar with that concept in statistics, a frequentist approach? So you're not interested in a probability distribution. And that means that essentially we are happy with fitting the data to a specific model, and then we want to use that model with some confidence. That's the standard path in machine learning. Generative methods, on the other hand, they give you the predictions, you fit a model, They allow you to find correlations in the data set. You can do that with discriminative methods as well and a frequentist approach. But it gives you also a probability distribution. And you can use that probability distribution to generate new data. And you can do that with a standard frequentist approach as well. But with a probability distribution, you have a statistical estimate of the errors, which you don't have with a standard frequentist approach, I mean the straightforward one. You can extract a probability from that one as well. But the generative methods, they allow us to make predictions, find correlations in the data, estimations of errors, and also look at causation. What is the probability of A given B? Because you have a probability distribution. And these methods, what they do then, they take training data, but then you generate a probability distribution. This is the essence of generative methods. And one of the standard ones, I mean, one of the first ones which was introduced are so-called Boltzmann machines. Is everybody familiar with the Boltzmann distribution? Good. That's is a method which has seen a revival because, you know, the Boltzmann distribution goes like the exponential of some argument multiplied with minus. And that in statistical mechanics, this argument has normally been the energy of the system times temperature or something like that, just to make it dimensionless. But you can replace that with a convolutional neural network, for instance. And then you can train a probability distribution. And these methods have actually seen a revival. But the problem with probability distributions is that they are really multidimensional. Even if you have an analytical expression for it, this can be a multidimensional quantity which is difficult to compute because you have too many variables. But this is the essence of generative methods. And then this other picture, I'm going to skip some of the blah, blah. You can read that yourself. The example here, when you do a discriminative model, if you do a classification problem, like a CNN, you're training on, let's say, paintings of Van Gogh, like here, and then you simply want to know whether this is Van Gogh or not, true, false. It's a binary problem. That's one of the most typical problems which we have. So then you train a model, and then you feed in paintings, and then you can decide whether it's a Van Gogh or not, with some classification precision, depending on the quality of your model and the amount of data you have. So this is a typical distinction between discriminative and generative methods. To me, generative methods are the interesting ones because I want a probability distribution for what I'm doing. That does not mean that a neural network is not a generative method. Because when you solve a differential equation with a neural network, you produce a solution. And you don't train it on labeled data. You're just solving a differential equation with a neural network. So you generate a solution. And if that solution, if you do quantum mechanics, then the solution is the wave function, and the wave function squared is the quantum mechanical probability. So I can use a standard discriminative method like a neural network also as a generative method. So the kind of transition between supervised, unsupervised is always a little bit floating. So don't take these kind of distinctions literally, because there can be floating transitions. This case here is clearly a discriminative case. You train on labeled data, and you want to then classify whether that is a Van Gogh painting or not. If I were to use a neural network to solve Schrödinger's equation, then I would actually generate a solution, and that solution is a probability distribution. So the distinction doesn't need to be that sharp. And I wanted to say a little bit about the kind of taxonomy of these generative deep learning methods, because in some cases you have an explicit expression for the density, and you approximate it in some way. And these are methods which approximate the probability distribution. So the target is the probability distribution. And you know that when you have a probability distribution, you can calculate standard deviations, You can calculate other expectation values, etc., etc. And in many of these programs like DALL-E, which makes images, this is the basic ingredients which enters. And then we have other ones like tractable densities. So when I say approximate densities, it's simply because your density may live in a tremendously large space, and it can be difficult to handle directly, even if you have an analytical expression. And then you need to approximate. And then you have tractable densities, and we are going to discuss a little bit about autoregressive methods. And then we have implicit densities from generative adversarial networks, which we will also discuss. So these are some of the central generative methods. And I think now it's time just to take a small break. I wanted to use the first hour to lay out the possibilities. And as I said, for you, it's more now to think what you want to do, why you are here. If this course is actually interesting for you, I don't get offended if you don't find it interesting. But this is something which I want you to think about till the next week. So as I said, we can discuss it after this next lecture as well. Say again?
The group session next week?
Yeah.
When is it?
From after the lecture, from 2 to 4. No, sorry, 12 to 2. 12 to 2. Sorry. Okay, let's take a small break, eh? So I wanted to give you in this lecture kind of a very, very quick overview of some of the basic elements and also some of the basic ingredients in a neural network. So this is more meant as a kind of a very, very quick reminder of something which we normally in other courses would spend a month on, or even have a long project. I hope you can forgive me for not going into all those details. But if you're a little bit on a shaky ground here, I have lots of material you can look at. Okay, so in machine learning, in essentially all the methods we deal with, irrespective of whether that is linear regression, you fitting a polynomial, or using random forests, ensemble methods, whatever kind of method, we have a data set, we have a model, and I normally like to fit a likelihood function, a probability. And you're probably familiar with this notation here, where this is a probability of X given alpha. And this is the typical situation when you deal with generative methods. Alternatively, you would like to fit a simple model, which is a function. It could be a continuous function, or it could be a discrete function. If you're dealing with a classification type of problem, it's a discrete function, which you often end up with. Then you would typically have outputs, true, false, yes, no, 1, 0, or whatever. It could be a binary case, or it could be a multi-class case. And then we have a function, which is the so-called loss function or cost function, or sometimes it's called the risk function. I often like to call it the error function, because when I solve differential equations, I often take the difference between the left-hand side and the right-hand side of the equation. And if that difference goes to 0, I have the solution. So I like to call that the error function. So the name is often something you will find being different from field to field, but I will try to be consistent, and I will often call it for the cost function. The loss is often referred to the individual contribution to the cost, but then people have more or less got used to call this for the loss function as well. So it varies from field to field. But it shouldn't be a problem with understanding what this function is, and this is a function we optimize. And at the heart of all these methods, there is an optimization problem. And as I said, one of the possibilities for the projects is actually to look at optimization algorithms, because that's really the big problem in machine learning. Now, if you train neural networks or CNNs or any of the generative methods, some of you may have heard of something which is called the barren plateau problem. Does that ring a bell? So one of the problems when you train gradients, because you have calculated the gradient of that function, and you're driving the gradients to zero. Now, in the training, if the gradients become zero too quickly, which means that the gradient is flat, so it's a barren plateau, then your training stops and you don't get any meaningful results. So what you often have, and this is linked with a very hot topic, which is called explainable AI, is that sometimes the fact that you get these gradients for some of the parameters which go to zero is because some of these parameters are just irrelevant for the scientific problem. So I see that when I do quantum mechanics. So when I do quantum mechanics, I have something which is called the intimidating quantity, which is called the Hilbert space, which can be monstrously large. And what you often want to do in quantum mechanics is to find the relevant degrees of freedom. So if I have a multi-billion space, maybe it's only 10 degrees of freedom, which are relevant. So what I will often see then is that the irrelevant degrees of freedom, they behave in a kind of chaotic way and can give gradients in the training, which just go to zero. So there's a lot of interesting explanations concerning the optimization problem. So as I said, the optimization, if that is something which triggers you, this is something which people actually have used as a topic for the projects. That was a digression, okay, on the optimization part. The data set is typically something, so I'm just setting up some of the basic mathematics here. So this is the typical data set if you have a vector with some entries, and then you have an output which you want to model. And if you're dealing with a regression problem, then you assume that there is a function which is continuous, looks beautiful, everything. Often we do fit neural networks to discontinuous functions. Sometimes we just hide under the carpet the problems, and we assume that we can use it. And then you can assume that there is a noise. That's a basic assumption when you do a regression problem. And that's the kind of assumption you often have in all types of data. So regression is actually you, in the simplest cases, you fitting a continuous function to your data set. So this is just a quick reminder. And one of the standard methods, and this is something which was basically developed by Gauss and Laplace and many famous mathematicians in the 18th century. And in that case, one assumed that there is a linear dependence on the unknown parameters. So where these are the parameters. These could be the parameters of a polynomial fit, where these are the coefficients in the polynomial expansion. And then you have a linear model where this is your data, the input data. This could be the x values of a function multiplied with this one. And this y tilde is a notation I will use for the model which you have made. So this is your model. Now, in this specific case, you can actually, with this function here, which is the mean squared error, which probably everybody has seen, which is a famous function. So when I solve differential equations, what I typically do then is to square the difference between the left-hand side and the right-hand side of a differential equation with a trial ansatz. And this is the cost function, which you then want to optimize. This y tilde is your output. And this is actually in statistics, this is something which you would call as an expectation value of the sample. It's a sample expectation value. So you have a sample of data. This doesn't need to be the true expectation value, but this is the sample expectation value. And you will often see this written as an expectation value. You simply take the difference between the data set you want to reproduce, what your model is giving, y tilde, and then this can be translated into a matrix and X with the vectors Y, and you can then optimize this and you have analytical solutions for the parameters. Now, this is something which I always say when I teach machine learning, is that you may ask yourself, where's the machine learning here? Why do we introduce linear regression in a machine learning context? You will see this basically in every textbook on machine learning. And there are several reasons for that. One is that you have an analytical expression where you can solve by matrix inversion, and you learn. So the learning is now given by you being able to invert this matrix and perform the matrix vector multiplications. So you would say then that you implement the algorithm and you learn the coefficients which optimize this quantity here. And obviously the ideal is a mean squared error, which is 0, because then you have a perfect fit. And what you would do is to calculate the optimization part is actually you taking the gradient of this quantity with respect to these parameters theta. So that means that if you have 100 parameters, you need 100 derivatives. And then you're optimizing those. And when you optimize those, this translates into a famous equation. Now, for those of you who are a little bit more familiar with this topic, you know that you can also derive this from a probabilistic point of view. So you can set up a Gaussian distribution for the quantity y, assuming that they follow a Gaussian distribution. And then you can optimize the distribution by maximizing the probability. If you do that, you get exactly the same equation if you just start with what you had on the previous slide in simple linear algebra terms. So linear regression is nice because you can sneak in the probabilistic interpretations. You can set up standard deviations of the parameters, etc., etc. So you can catch many, many birds with just one stone. And that's why you will often see this very simple method as an entry point to machine learning courses. So I use this just to remind people of some of the basic elements. Okay? Now, the next thing you would typically do then, when you optimize this, is that you can change the expression. So typically what you would do is to rewrite this one in terms of a more compact formulation where you have the norm 2 of a vector, which is defined like this. So this is just the norm 2 here. You're calculating an inner product because the mean squared error is just a number. So it has to be an inner product. And you can then add terms here. So how many of you are familiar with hyperparameters and region lasso regression? So how many of you heard of that? Excellent. So what you're doing then is that you're optimizing another function. This gives you much more freedom to actually find a minimum of the cost function. So when we are going to do physics-informed neural networks, the function you see here, which looks like the mean squared error, is going to be the difference between the left-hand side and the right-hand side of a differential equation, plus an addition which reflects the boundary conditions and initial conditions. So you're getting what's called a cost function, which is a little bit different. Now, in neural networks, you don't know whether the plain mean squared error is the one which gives you the ideal representation of the data. So adding these hyperparameters, lambda, gives you additional freedoms in tuning a multidimensional object in order to find the minima. So I'm trying to stay at this more kind of overarching point of view. And I hope that many of the things I'm saying rings a bell, because you've probably seen many of these concepts before. But please ask and interrupt me if this, what I'm saying now, is unknown. But what you end up with is a different optimization problem. So some people get disappointed when they see that machine learning is just parameter tuning. But what you're doing is that you're baking in all your insights about the problem in terms of this cost function. So it doesn't need to look like that. This is a function where you would tailor that one according to your problem. And as I said, when you do physics-informed neural networks for solving differential equations, you can have something which looks like the mean squared error, but then you would add to it in the optimization part, the boundary conditions and the initial conditions. And that's where you bake in your physics. or your knowledge about the system. So one thing is the equation itself, which governs the laws of the system, but then the specific case is dictated by the boundary conditions and the initial conditions. Does that sound okay? Okay. So this actually, if you do regression in the linear regression, from the linear regression point of view, this leads to what's called ridge regression. And then you have lasso regression, where you have another type of hyperparameter defined cost function. So then we're optimizing this problem. And then you can get more and more complicated cost functions. So the cost function or error function, or what we call it, is something which you define. And you use your insight about the problem. So I just wanted to show you another problem. So this is where I am abusing a little bit by introducing my own research. So what I'm doing is to solve quantum mechanical problems, and I've been using neural networks to do that. And in the best quantum mechanical many-body method, the one which actually gives you almost the exact energies, is something which is based on Monte Carlo methods. And the standard gold standard is called diffusion Monte Carlo, but the variational Monte Carlo uses the variational principle, and it's actually you solving a multi-dimensional integral. And you do that, essentially what you're doing here is to solve a integral which is multidimensional. So if I have atomic neon with 10 electrons and I only you look at the electron degrees of freedom in 3 dimensions, this integral is a 30-dimensional integral. And there is no way you can use your favorite Gaussian quadrature method. You will simply, if you want to compute that with standard methods, you will need, to get a decent precision, more time than the lifetime of the universe. No, not the lifetime of the universe. The universe time. No, what do you mean? Lifetime of the universe. I think that's okay. Yeah. So what is it? The lifetime of the universe? Anyone who knows that? These are the kind of numbers you should know by heart, right? If you get stranded on a remote island, the only book you need is the physical constants, the table of that. Sorry. Yeah?
Sorry.
So, how many seconds? Anyone who remembers that? Roughly 10 to the 18th, I think. That's the estimated lifetime of the universe. So if you want to get a precision for that integral, which is decent, with 100 integration points in every direction, and use standard methods, you would need more time than the time of the universe to compute that. That's why Monte Carlo methods are used. And the whole thing here is actually that you want to use a trial function which encodes all your physics. So the question is, why not use a neural network to express this function, where the only thing you bake in are the essential symmetries? So that's, again, a physics-informed problem. And neural networks do a fantastic job. It actually beats all the traditional many-body methods. And what you typically do then is that you rewrite everything in terms of a probability distribution, where this alpha are now the constants of the neural network. And you can have millions of these parameters. And then you evaluate this integral as a function of these parameters. And then you calculate the gradient of this quantity with respect to the parameters. And that's essentially how you would use a neural network here. And then you just start with a guess, and then you let the network optimize the energy for you. So the cost function now is this one. It's not the mean squared error. The cost function or the loss function is the expectation value of the energy. And you see how things changes, but the thing which is nice with a neural network compared, so how many of you are familiar with differential equation methods like finite difference and finite element? And there you know that if you're changing dimensionality, if you're changing equation, you often have to change the method, right? If you do a diffusion equation in 1 dimension, you use 1 method. If you do it in 2, you would often call iterative methods, etc., etc. When you use neural networks, they are agnostic to dimension. They are agnostic to the type of equation. You would just have to bake in the boundary conditions and initial conditions. And the same here, when you do a standard calculation, you often use a pretty complicated analytical ansatz. But now you can just let a network which contains the essential symmetries of the problem. And then you take the derivatives. I'm not going to go through everything here, but this is roughly the derivative of the energy, this E bar here. And this I is one of the parameters. And you have to evaluate three integrals, where this is just a derivative of the trial wave function. And I just wanted to say a little bit about a neural network and then show you some results, or rather, I can show you the results first. So this is the calculation with a neural network for the electron gas. Is anyone familiar with the electron gas? That's a standard benchmark problem in physics, the homogeneous electron gas. It's an infinite system of electrons, which then are surrounded by a continuous background, which mimics the ions in a, let's say, a semiconductor or a metal or whatever. And this bar here is the diffusion Monte Carlo benchmark. This is the best theoretical calculation. And this is calculated with a neural network where the only input are the symmetries of the wave function. And since these are electrons, the wave function has to be antisymmetric. And this is the number of iterations when you do a feed-forward neural network with a backward propagation, the back propagation algorithm. So it's a feed-forward step and a back propagation step. And this is a number of steps which you make. And this is actually without any other knowledge than just essential symmetries. So let me say a little bit about why neural networks are so important. Have you heard about the universal approximation theorem? So the universal approximation theorem, basically, when you do a fit to functions, like when you fit a polynomial, you may have heard about the Stone-Weierstrass theorem for polynomials, which gives you an error estimate. If you use Fourier expansions, you have similar error estimates on how well a Fourier expansion represents your data. So the universal approximation theorem states that a feed-forward neural network with just a single hidden layer containing a finite number of neurons can approximate a continuous multidimensional function to arbitrary accuracy. So what this accuracy is, we don't know. It doesn't say anything about how many hidden layers you need, how many nodes in the layer you need. It just simply says that you can approximate a continuous function to a given accuracy. So Sybenko and Hornik developed this for just a non-constant bounded and monotonically increasing continuous function, where the activation function is given by that. Now, some of you are familiar with other activation functions like ReLU. So how many of you have heard of that? That is not a bounded function. So this statement, this is the original one from Sybenko. This is actually modified a little bit. And there are some additions here to the theorem. So while basically technically correct, it omits some details and is not the most general form of the theorem. So what you see there is the original one, which was tailored to the sigmoid function as an activation function. But then a more precise phrasing is for any continuous function on a compact domain in R to the n and any error, there exists a feed-forward network with one hidden layer and a suitable activation function, which such that the network's outputs uniformly approximate f with an error epsilon. The classical theorems normally says non-constant, bounded, and monotonically are sufficient, but not necessary. And these actually are things which have been modified later. So it means that functions like the ReLU function, which is actually non-bounded, is a function which can be used. And one of the things, if you're interested in doing the mathematics of neural networks, what people have typically done in such a project is to explore also different activation functions for the specific problems. And there's a ton of activation functions. You have JELU, CELU, ReLU, ELU, etc., etc. So the whole thing is that what you want is an activation function which is easy to calculate, and has nice analytical expression for the derivatives so that you can use automatic differentiation. So are you all familiar with automatic differentiation? Roughly. So automatic differentiation is the one which saves your day because you don't need to write down all the gradients by paper and pencil and code them. Yeah, there are some basic statements here. So there's a basic extension here, which came in 93, which provided a feed-forward network as a universal approximator if and only if the activation function is not a polynomial. So that's an important extension. So a neural network, if you go back to these results here, if you now, in this case, we know that the diffusion Monte Carlo is probably the best result. The neural network functions as a universal approximator for you. It doesn't tell you that you will get this and this error, but it tells you you will be able to approximate a function, a continuous function with a given error. And then it's you who has to decide what is the best result. Okay? So this is the way I want you to look at the neural network as a universal approximator, where you can then start with an ansatz where you bake in as much information as possible about the system. That means that your specific discipline-based knowledge plays a central role. And that applies to the way you define the cost function and how you assess if the result's okay or not. Questions, guys? So I'm just giving you a kind of crash course on neural networks. I just wanted to bring up some of the basic equations. Is that okay if I do that? So just a quick reminder. And then there is some homeworks as well, where you have to reboot your memories and look back at what you've done. Yeah, I'm going to skip this one, actually. Let me also skip these. I wanted to say a little bit about the neural network, and just to remind you of the basic elements. So when you fit a polynomial with linear regression, the degree of the polynomial is your model. That is you who decides what the model looks like. Now, with a neural network, the model is the architecture of the network. So that means that when you fit a function, and if you insist on feeding in a polynomial approximation to the function, the network will fit a polynomial for you of degree 5. But your data may be a polynomial of degree 10. So that means that you should let the network find the best approximation without telling it that it should be a polynomial of degree 5. Okay? So the architecture consists of these different elements. So it has an input and output layer, where the input is defined by obviously input X, and the output produces a model Y tilde, which you then compare to the target value. So in my notation, Y tilde is going to be the typical output of your model. Then there is a given number of hidden layers, which become parameters. Then you have an activation function, and the activation functions could differ from layer to layer, but they can also be the same. And that's pretty common, that you use the same activation functions for all the hidden layers, and you have a different activation function for the output layer, which then reflects the type of problem you're looking at. So if you want to have a binary reproduction, a binary problem, yes, no, 1, 0, you have just one output. But you could have thousands of inputs. If you're looking at an image and you want to distinguish where, or painting, if this is a Van Gogh or not, that painting may have 200 times 200 pixels. So you would have 40,000 input nodes, and you just have one output, which is yes, no, Van Gogh, not Van Gogh. So that would be a typical training. And then you have perhaps 100 paintings of Van Gogh. So this means that the output layers may be different from the hidden layers. And then you have, as we say, has normally an activation function tailored to the specific problem. And then you have a cost function. As I said, when I do quantum mechanical studies, I often actually either look at the difference between the left-hand side and the right-hand side of the differential equation and square that. That's my cost function. Or if I do this Monte Carlo calculation, it is the expectation value of the energy with a given guess for the wave function. So I'm using this kind of examples because this is the kind of research I'm doing. But the neural networks are actually agnostic in a sense to the type of problem you're dealing with. If you have a neural network, you define different cost functions, and then you can actually use that on a plethora of problems. So it's a universal approximator. That's very important to keep in mind. And the reason why I'm stressing this is that neural networks actually are the building blocks in many of the other methods. So when you do a recurrent neural network at every time step, inside there is a neural network. If you do a convolution neural network, there is inside a neural network code plus a little bit more. If you do autoencoders, the simplest form is actually take a neural network. If you're doing generative methods, you will often use neural networks. If you use Boltzmann machine, you can have a neural network as an argument. So understanding these is very central for basically all the methods we're dealing with. So if you have understood the neural networks, you have the basic building block, which enters many of the other methods. And then the cost function is now the unknown of these parameters theta. And it's pretty common then to have weights and biases. So I'm going to show you in an image here. Let me just bring it up. So when you look at the typical neural network here, you have some inputs, which then feed in to the first hidden layer. So here we have a number of hidden nodes. We have 3 hidden layers. And these are connected by weights. Every hidden node, so this is the output from a given hidden node, what you see here. And the final hidden layer feeds into the output layer, and that produces these different outputs. So if you have a binary case, you just have yes, no, so just one node. If you have, let's say, the MNIST dataset, which many of you have encountered, which is a classic in all textbooks, then you want to classify 10 handwritten numbers from 0 to 9. So then you would have 10 classes and 10 output nodes. So these are the outputs from every layer, every node in every layer. And what you do here is you feed in some input information, which I'm going to set up quickly now for you. So I also wanted to say a little bit more about the other ingredients. So the standard way is to use gradient methods. And this is about the optimization part. So if somebody's interested in studying that in the project, there's a lot of interesting mathematics to look at. But the plain methods to do the optimization is plain gradient descent with a learning rate, which is a way to circumvent the calculation of second derivatives. So the second derivative is given by a Jacobian matrix. And if you have 1 million variables, that matrix is going to be a matrix of dimension 1 million times 1 million. And when you do a gradient approximation, then you use Newton's method. So actually all these methods, which you see here, are based on Newton's method. Is everybody familiar with Newton's method? That's a basic method for finding the roots of a function. So we are driving the gradients to 0. And then we have Newton's method, which is a truncation at second order in the derivatives. And the second derivative is this Jacobian matrix. So it's the second derivatives of the cost function. And if you then have, as I said, 1 million parameters, at every iteration, you would have to invert 1 million times a 1 million matrix, and you don't do that. And you replace that with a parameter which is called the learning rate. And then you explore different parameters. And there are many, many ways of doing this. And there are ways to update iteratively the value of this learning rate. And these methods, which you see here, adaptive gradient, root mean square propagation, and ADAM, they are some of the most popular ones. And for those of you who are familiar with the field, the guy who actually developed ADAM, it's called Kingma. That paper came in 2014, and it has now more than 200,000 citations. This guy also invented variational autoencoders, which has something like 70,000 citations. My best paper has 1,300 citations, which is decent for a physicist, but it's no way you can compare with what happens in this field. It also tells you, and you probably heard that kind of joke, is that if you want to get many more friends, if you do some improvements on these methods, you will get many friends, and they will cite you. And I'm not inferring that you don't have friends, but you can think of this is really the bottleneck of basically all machine learning, the optimization part. Okay, so let's just move on here. Yeah, then we have additional hyperparameters, and this will be discussed a little bit below here. So typically, this is the cost function, and the equation which I'm doing now is actually based on the plane regression case. And what I've done here is actually to set up the equation, the general ones. But if you feel that you need to refresh things, if you go back to the lecture notes here, or you go back to courses at the Department of Informatics, then you will find in-depth discussions, and the notes from week 41, 43 give you many of the details, starting with a scalar input, scalar output, 0 hidden layers, 1 hidden layers, etc. And you see how you set up the equations for the derivatives. So the algorithm which you're doing them is based on you feeding in an input here. These inputs are linked with the first hidden layer through parameters we call weights, and something we call a bias for every node, which is offset to be non-zero, to hinder that some gradients are by accident set to 0. Because if the gradient is set to 0, the training stops. So what you typically do then is that you feed this information through the net. You initialize these parameters by random values. The initialization itself is a big issue, by the way. And Ben Joe, the guy who gave the seminar last year, is actually one of the people who actually found what was the problem with the initialization of the weights and biases. Actually, that is seen as a fundamental paper in deep learning, because many of the deep learning algorithms, they were viewed with, let's say, less excitement than they are now, before 2010, when Ben Joe's paper came, because the training of the network was often stuck. The gradients would go to 0. And that had to do with both the initialization of the weights and biases and the activation function, which was the sigmoid, the standard one, very much inspired by research in neuroscience. So we typically call the beginning of the deep learning revolution roughly around 2010. That's really when these things took off. And then with convolutional neural networks as the classic example for image recognition, then the field just exploded. And you see the development. So we typically say that the deep learning revolution started roughly around 2010, but the methods had been around for 30, 40 years. So actually, when I started my PhD back in the 80s, then people were starting to look at neural networks because Sybenko came with a theorem about the universal approximation. And that spurred a lot of interest in neural networks. But a lot of the implementation were a little bit stuck because we had simply problems with the training. And also, there was less access to high-performance computing facilities because the training requires a lot of resources. So the typical way we do that, and I'm just going to go a little bit quickly through this so that you can look it up again, is that every node in, let me just go quickly back. So every node here receives an input, which is now given by the parameters, the weights. This is the output from the previous hidden layer and a given node A. And then you have a bias, which is set up to offset in case the gradients can become zero. So this would be the input to a node J in layer L. Then a typical activation function, this is an example. So the output is then given by this activation function, and this is the sigmoid function. That's the classic one. And it's also been an activation function which people are still using. And in some cases, it can actually, depending on the science you're doing, it can be a relevant function. But I'm just putting it up here as an example of an activation function. And this is the one which Sybenko and Hornig used when they derived the universal approximation. So this is the output. So this A, which you see here, is the output from a node J from layer L. And if you go back then, that means that this output from the first node in the first hidden layer is then fed into with a new weight and a new bias here into the first node in the second layer, the second node in the second layer, and all the other nodes. So that's fed in, and this is set up as you can see here, as a matrix times the output from the previous layer plus the biases. So this will be a vector, and this is then obviously matrix times a vector, which becomes a vector. Okay? Now I see many people nodding because you coded this, and there's always quite some struggle in doing that. And the kind of things you need now, so if I just go back very quickly here, so we have a feed forward stage, which then gives a final result. Now, this final result is then compared with the target value. And then we calculate the derivative at the output layer. But when we have the derivative of the output layer and the gradients here, we also need to propagate back and get the gradients here, the gradients here, and the gradients here. So then we have an algorithm for propagating back, which is nothing but the chain rule for derivatives. So mathematically, if you want to be very, very arrogant, and I am a physicist and we often tend to be arrogant, is that neural networks is nothing but matrix vector and matrix multiplication and the application of the chain rule, which is roughly high school physics, mathematics, right? That's a very arrogant statement. But if you want to really nail it down to simple mathematical operations, chain rule, which allows you to use automatic differentiation and matrix vector multiplications. So then when you are finding the derivative, so the back propagation algorithm is nothing but you finding the derivatives, the gradients, for every single node by using the chain rule. Okay? That's essentially the mathematics. And the details which I bring up here are details which you also have in the other lecture notes from the previous course. And what I'm setting up are all the different derivatives which are needed. So as a function of the different layers, so this is layer L. It's actually, this is the letter L, it's not 1. That allows me to crack a joke. It's actually, I wasted 3 weeks of my life because I used a programming language called Fortran, where you don't need to declare variables. And I had a variable, if you look at L here, and number 1 on the keyboard, they look very much the same. So I had somewhere in a program of 50,000 lines, I had a 1 which had become an L. It took me 3 weeks. After that, I declared all variables. Okay. But this is N. And then what we have then, when we do the different derivatives, we calculate by the chain rule. So we would have the derivatives at the final layer for the weights, and we can find a similar one for the biases. And this will be tailored now to the specific activation function, which you have. If you have the sigmoid function, then this becomes equal to that, but these are the outputs from the final layer, which are actually this y tilde. You can see I've changed the y tilde to match that figure with this L, which is the final layer. And then what you need is to set up the derivatives. And when you have the, I'm going a little bit fast here. You need the derivatives in order to find the different expression for the gradients. So I'm going to rush a little bit through, but I will pick this up next week. But what you can do then at the end is that when you have all the derivatives, you can set up the gradients for the update of the weights and the biases. And these expressions which you get then for these different terms, this term delta here, which now has a mathematical expression in terms of the previous layer, and then the weights and the derivatives of the activation functions. These are generic expressions for neural network, which then give you all the derivatives, which you then use for every single node and every layer to update the parameters. And these are the parameters you have, and these can be millions or billions of parameters which are training, depending on the size of the network and the number of nodes, number of hidden layers, etc. So these are the basic expression, which then gives you the derivative, which are then trained by feed-forward and backpropagation. And the final thing is that when you do the training, you don't want these gradients, because if you look at the function you're optimizing, this is the function you want to drive to zero in this specific case. So if a specific gradient here becomes zero, then the training can stop. And that's called the vanishing gradient problem, which has been a problem which has been a plague to basically all implementations. But the gradients can also explode, and there is something called the exploding gradient problem. So the training itself is actually a pretty delicate thing. And this goes again back to the type of projects which we can do. So if you're interested in looking at more the mathematical aspects of a neural network, these are things to explore and study in a project. And this, people who have done that, they've often used the whole semester on just the mathematics of deep learning. So that's a possibility. I apologize for rushing a little bit through. I will pick up these things again next week. But when you're setting up the backpropagation, I just need to sneak in 1 or 2 more minutes. You have set up the input data and the activation functions, and then you calculate the pertinent outputs. You perform then the feed forward till you reach the output layer, and you compute all these inputs of the input layer and compute the activation function and the pertinent outputs. Thereafter, you compute the output error, which is given by these gradients. And then you come back propagate and you get this parameter here. And when you have done that, you update the weights and the biases using gradient descent for each hidden layer. And then you update the weights. So the backpropagation is an algorithm which gives you the derivatives. And then you use gradient descent to update the derivative. So every step in a feed forward and a backpropagation gives you one update. So if I do 1,000 iterations, I have done 1,000 updates of the parameters. Okay, so what I also have here at the end, and we won't have time to do that, but I wanted you to, so I'm sorry for rushing a little bit through these things at the end, but many of you have seen the basic equations. So what I want you to do now is actually to, for next week, revisit your own neural network implementations. If you haven't done it, I mean, there is a steeper threshold, but we will help you with overcoming that threshold. But then take a look at your what you've done. And you can also use the provided PyTorch or TensorFlow examples, which you can find both in this week 43. There's also an example on how you can write it from scratch, but many of you have done that already. So at the end of the slides for this week, I have a PyTorch example and a TensorFlow example. And these are things which I want you, as a part of a homework, to take a look till next time. So for some of you, this may be a little bit more, if you are not too familiar with it, it may struggle a bit more. But this is also what the lab sessions are for. And I hope you can understand that I cannot spend a month on going through neural networks, since many of you have actually done it. So we want to get into the more interesting methods for the rest of the course as quickly as possible. So take a look at these kind of small assignments the next time. And what I would, if you have time, if you want to hang around a little bit and discuss the projects, feel free to do that. Alternatively, we would like you to prepare some 3-5 slides, come up with ideas, use the week to think of what you would like to do, and then even have a presentation. And what we did last year was actually to, and the year before, was that these presentations, we would put them on GitHub so that people can look them up. And they say, hey, I like your project. Can I join your group, right? That's because not everybody, people don't know each other here, right? Yeah. Yeah, so if you, but we haven't, I mean, not everybody is able to finish it by next Thursday. Then we can use the lab session the week thereafter. So, but we would like to get started as quickly as possible. So take some time to think of what you want to do, given the different possibilities you have. Yeah, that's wrong. Okay.